Hello, everyone. I hope you're doing well. First of all, I'm so sorry that this review session was delayed. So here I am. I'm here to provide a review session for the final exam. Okay, so let's talk about the final party. So based on the university schedule, the final is going to be on this Thursday, from 12 to 2 p.m. So final party, final exam, right? And this is April 30th, Thursday, from 12 to 2 p.m. That is the original schedule. And like the midterm number 2, I'm going to give you 50 more minutes. And this is the time that you are going to take a picture of your work and then convert it into one PDF file and submit it on the Blackboard. So during this 15-minute, combine everything into one PDF file and then upload it on the Blackboard. And we did the same thing for midterm number 2. I didn't see any major problems, so I'm going to assume that it's going to be smooth again. Okay, and this is open book, open note, whatever open material testing. So you can use your material, and then you're going to use a calculator, of course. And this is a comprehensive exam, which means it will cover everything. So chapter 7 through 7, 8, 9, 10, 11, 12, 13, 14, 15. So 7 through 15. And then we skipped 16. And then the last chapter is chapter 17. And by the way, this buckling failure, the buckling of the column, this chapter, I'm going to provide one bonus problem, the extra point problem from chapter 17, because we didn't cover it on the entertainment package. Okay, so I'm going to go over chapter by chapter. By the way, chapters 10, 11, and 15 were covered by midterm number 2, and you can see the review session for midterm number 2. So I'm not going to cover those 3 sections in this video. So let's start with chapter 7. So chapter 7, this is about stress and strain. So you might remember that the first lecture of this class at the beginning of the semester, we started with the definition of stress and strain. Those are the main topics in chapter 7. We have 2 different types of stresses and strains. One is a normal stress and normal strain. The other one is a shear stress and shear strain. And we use sigma and epsilon for normal stress and normal strain, and tau and gamma for shear stress and shear strain. So this is the normal or actual stress and strain, and this is for shear stress and strain. How can we differentiate normal stress strain versus shear stress strain? It is depending on the direction of load. So normal means perpendicular to the cross section. Shear means the parallel to the cross section, okay? And the mathematical formulation of this normal stress and normal strain, sigma, is defined as P over A. So this sigma is the amount of the force, the intensity of the force, right? P is a force over the cross-sectional area. So, and this P, the force should be the normal force, which is the direction of the force P is perpendicular 90-degree angle to the cross section. And epsilon is normal strain. Normal strain, by definition, this is a rate between 2 lengths. One, the deformation, and this is the deformation along the length of the member. And this L is the original length, okay? So we talk about the normal stress, normal strain, tau is the shear stress, and we always put the average sign for tau. The reason is because this sigma is equal to P over A. This is also the average value, but except the case that the force is very close to the edge of the member. So when you're away from that edge, the sigma average is more or less the same as the sigma. So many times we just ignore this average sign for normal stress, but the tau, this is totally different. It is very nonlinear behavior. So we have a nonlinear distribution. So it varies from 0 to the maximum value. So that's why we always put the average sign. And the definition is similar, V over A. So V is shear force, A is the cross-sectional area, and gamma is the shear strain. So that is measured in an angle. So I showed you, right? So when we apply the shear force, so let's say this is the cross-sectional area, we apply this force parallel to that cross-sectional area, and we can measure the angle difference. As you can see, this angle difference, right? So that is the gamma. Okay, so those are covered in chapter 7. And by the way, to solve the problems in chapter 7, you have to understand the fundamentals that we studied in statics. For example, free body diagram. You have to understand how to draw a free body diagram. Free body diagram is a diagram of freed body which is isolated from its surroundings. You also have to have an understanding about the equilibrium equation. Okay, so equilibrium equation for 2D analysis, we have sum of forces in X is equal to 0, sum of forces in Y is equal to 0, and the moment is equal to 0. So we will have 3 equilibrium equations, right, to solve up to 3 unknown variables. We also talk about the factor of safety at the end of this chapter 7. Factor of safety, this is a safety margin. So it is a ratio between the real failure to the allowable value. Or we can also say that this is in terms of the stress value, sigma failure divided by sigma allowable. Okay, so that's the definition of factor of safety. Practice problem for this chapter in this content. Here we have the 7.6, 7.8, 7.10, and 7.14. Okay, so these are the example problems in the textbook, plus entertainment package problems will be the good starting point and the good practice problem. In other words, if you are familiar with these problems, at least, then you should be able to solve the problems from chapter 7 on final. Okay, let's move on to the next chapter. So next chapter is chapter 8. So we studied stress and strain, the definitions of those two quantities in chapter 7. Chapter 8, the title is Mechanical Properties of Materials. So basically, we started with learning about the relationship between stress and strain. So sigma and epsilon, or tau to gamma value. How can we see that? The very basic is this. So, for example, here we have a specimen that we'd like to know the material properties. When you apply the actual force, the normal force, okay? So let's say that is P, and we can easily find out the cross-sectional area before we apply the force. And then we measure the deformation. This is the actual deformation delta. Okay, then what we can do is we can see the relationship between, first of all, this P to delta. When we applied a certain amount of the normal force, the elongation, when we apply the tensile force, then we will expect to have an elongation, right? So that we can kind of apply for. So this is from P to delta. Initially, we have a linear proportional relationship. After that, it can go nonlinear. When you have this P delta relationship, so actual force and corresponding elongation relationship, we can now see the relationship between sigma and epsilon, because the sigma is defined as P over A. A is a cross-sectional area, while this epsilon is delta over L. L is the original length of the specimen. Okay, so if we measure and monitor the relationship between P and delta, then that relationship will be exactly the same as this sigma epsilon relationship. And this sigma epsilon relationship, this relationship tells a lot of things. First of all, we can easily find out the initial proportional relationship between the sigma and epsilon, that is called the Young's modulus, okay? And then we can have a point that the behavior is changed from elastic behavior to inelastic, nonlinear, or plastic relationship. And that is defined by the yield point. So that is called the sigma y. We can also see the ultimate strength of the material, that is sigma ultimate, sigma u. Okay, so these are the kind of important mechanical properties to identify a certain material. And we talk about the sigma epsilon relationship for mild steel. And by the way, each material, every material has a different the relationship between sigma and epsilon, and this is a kind of a typical relationship between sigma and epsilon for mild steel. Okay, so we have a very clear linear proportional relationship reason that is called linear proportional elastic reason, and this is yielding. So this is elastic, this is yielding. From here to the maximum value, we called strain hardening, and then after that it is necking reason. So this one, the corresponding stress value is called the sigma y, the sigma u. This is sigma u, the ultimate value, the maximum value. The sigma value corresponding to the borderline between elastic and everything beyond this yield point is called inelastic or plastic reason, and that is sigma y. So elastic reason means when you apply the force and remove the force, it goes back to the original position. So we are going back and forth like this. But beyond this yielding point, it doesn't go back to the original position. When we remove the force, for example, at here, it will go back this way. So this slope is going to be parallel to the initial slope, which has this slope of E, the Young's modulus. So at the end, we will have a certain plastic deformation after all. Okay, so we talked about that. We can also see the relationship between this tau and the gamma. Tau is the shear stress, and the gamma, I said, the angle change due to the shear force. We also talked about the Poisson's ratio. Poisson's ratio, we use the nu to define this Poisson's ratio. And the Poisson's ratio, by definition, this is the ratio between two different strains. The numerator, that's the strain in the lateral direction. the denominator, it is a strain along the longitudinal direction, along the length of the member. So for example, when we have a member and apply the axial force this way, we expect to have a, the shortening in the lateral direction. So this is the longitudinal direction, this is the lateral direction. Whenever we have an elongation in one direction and the other one should be the shortening, and vice versa. That's why we put the negative sign in the formula to make this new value as a positive always. We also talk about, so I just explained the E, the Young's modulus. That's the initial slope between sigma and epsilon. Sigma is the normal stress, epsilon is the normal strain. We can also see the similar relationship between tau and gamma, and the initial slope we call this shear modulus, G, or modulus of the rigidity. And there is a relationship between, among these three quantities, Young's modulus E, shear modulus G, and the Poisson's ratio nu. And this looks like this, E divided by 2 times 1 plus nu. So for example, when we have a problem and the material properties of shear modulus and Young's modulus are given and Poisson's ratio is not given, but you have to find out the lateral strain or longitudinal strain with a given condition, then you can use this equation. Or any other combination like Young's modulus and the new value is given and the shear modulus is not given, but we have to see the relationship between tau and gamma, and you can use this equation. Okay, the practice problem sets, examples 8.2, 8.3, and 8.5. These 3 problems from your textbook example problems, plus entertainment package problems for chapter 8. Okay, let's move on to chapter 9. So chapter 9, this is about axial load. So chapter 9, chapter 10, chapter 11, and later on, we were talking about different behaviors. So chapter 9 and chapter 17 as well. Chapter 9 and 17's similarity is we're talking about the axial load, okay? The difference for chapter 17, this is only for the compression, while this chapter 9, this includes both the tension and compression. So we talk about the behavior and how we can find out the corresponding deformation due to the axial load, whether it is going to be the compression or the tension. So the main equation that we use was this delta is equal to PL over EA. When we have a different loadings or multiple loadings or different lengths for each segment having different cross-sectional areas or the material properties, then we used the same equation, but using this sigma sign so that we can add up these PL over EA term for each segment, okay? Anyway, so for example, I'm just creating a problem. So let's say here we have one force P1, P2, P3, and we have a different diameters, diameter 1, diameter 2. Okay, then what we need to do is we have to break it into 2 segments here now. Let's say this is L1, L2, the length is. So when you make a cut and draw a free body diagram, when you make a cut anywhere in between these 2 points and draw a free body diagram, to see the P1 and P2. P1, P2s are internal forces for each segment. It may not be exactly matched with P1 or P2 or P3, right? You have to draw a free body diagram and apply the equilibrium equations to figure out those internal forces. So anyway, you can find out the corresponding delta or delta relative to a certain point using this equation. And one of the reasons that we studied this deformation in chapter 9 and 10, we didn't talk about the bending deformation in chapter 11, but like chapter 9 and 10, one of the reasons that we studied this deformation is because this deformation can be used to solve the statically indeterminate problem. Statically indeterminate problem means it doesn't mean that the structure is bad or there's something wrong. The only problem is we cannot solve or we cannot analyze this problem using the static equilibrium equations. Earlier I mentioned that for 2D problem we have 3 equations of equilibrium, which is the sum of forces in x, sum of forces in y, sum of the moment equation. So whenever you have more than 3 unknowns, that is classified as a statically indeterminate problem, because we have more unknowns than independent equations, number of equations. We have to have additional information, and that can be used as the deformation. So later this chapter 9, we covered how to solve the problem, the statically indeterminate problem, using force method. Force method is basically the idea of the superposition, right? So we remove the one unknown variable, the force, unknown force, and then we break it into 2 statically determinate systems, and then apply find out the expression of the deformations, and then set up we call the comparability equation. So that equation will serve as additional equation in addition to these 3 equations of equilibrium. So you can practice through these practice problems from chapter 9. I just 9.1, 9.9, and 9.10. So these are the example problems from your textbook, plus entertainment package problems will be the good starting point. Okay. All right. Again, chapter 10, chapter 11, and chapter 15. So those 3 chapters were covered in midterm number 2. So chapter 10, 11, and 15. I recommend you to watch the review session for midterm number 2 again, because is basically for these 3 chapters. So let's move on to chapter 12. Chapter 12, transverse shear. So in this chapter, we talk about the shear stress. The bottom line, the main equation for this chapter 12, is this: tau is equal to V Q over I T. Okay, so the best way to understand this chapter 12 especially, is going through the problems, example problems, and the entertainment package problems. But let me just explain what each of the term means. So tau is the shear stress, and V is the shear force. So we can find out the shear stress from the shear force. I, this is the moment of inertia. And we studied how to calculate the moment of inertia in statics, right? So basically, moment of inertia for the rectangular section is BH cubed over 12. If we take the moment of inertia about its centroidal axis, then this is the only equation. If not, then we have to calculate moment of inertia about its own centroidal axis for each rectangular section, and then add this AD squared term to find out the moment of inertia about new axis. Okay, and this T is the thickness where you calculate and you estimate this shear stress. And this Q is the first moment of area. So in your textbook, chapter 12, is y bar prime times a prime. A prime. So this y bar prime is the distance from the centroid of the main section to the centroidal, the area above the line, and then a prime is the corresponding area. So for example, let's say I'm going to show you the example, and this is the, let's see, okay, this is coming from page 563, the figure 12-6. So this is page 563. 563, figure 12-6. So let's say here we have a T-shaped section. It looks something like this. Okay. And then let's say we'd like to find out the shear stress at this level. Okay, then how can we calculate Q? That's my question. So I said Q can be calculated as y bar prime times a prime. So in this case, a prime is going to be the area from the top to the location where we are estimating the shear stress. So this top flange, this shaded area, will be a prime. Okay, now what is y bar prime? Y bar prime is this. So first of all, we have to see and we have to find out the centroid of this T-shaped section. So let's say we calculate the neutral axis, the location of centroid, and that's here. So this point is going to be the centroid of this entire T-shaped section. We can also find out the centroid of this A prime, right? The area, the shaded area above this point where we are estimating the shear stress. This y bar prime is the distance between these 2 points. Okay, so this is a neutral axis, which is passing through the centroid of the entire section. And this point is the centroid of this shaded area. So the y bar prime is going to be the distance between those two. There are several different examples in that figure, so you can easily find out and exercise how we can find out this first moment of area. And this Q is the most kind of confusing part. Everything else is the straightforward. So you can usually the shear force is given, and then find out the shear stress. Otherwise, you have a shear stress given, and you need to solve for shear force. Moment of inertia, you can easily find out the moment of inertia using these 2 equations. Thickness is the thickness where depending on the location. And for example, this case, we can have 2 different values for shear the thicknesses. One, let's say the same point, but let's say this is the bottom of the top flange, then the corresponding thickness is going to be the width of this flange, or the same point, but it is going to be the top of this web, then this value is going to be the thickness in that case. So that's why we will have a jump in terms of the shear stress at that point. Okay, and we went through the example problems for that. Okay, one last thing is the shear flow. So we also talked about the shear flow. Shear flow is this. This is the definition of shear flow. So the only difference between the shear stress and shear flow is this: the shear stress we divided by thickness again, and the shear flow doesn't have any thickness. That's why the units are different, and the definition of shear flow is the force per unit length, okay? Okay, so with understanding of those definitions and the equations, I recommend you to solve for 12.1, 12.3, and 12.4. And these problems are solved, and the solving these three problems are already recorded and uploaded on the Blackboard, so you can go through those video clips again. But these are the example problems in the textbook, and plus entertainment package problems. So this is the main topic of chapter 12. Let's move on to the next one. Chapter 13 was really kind of a simple chapter about thin-walled pressure vessel. And there are two different equations, and I explained about that. One is the case with when we have a cylindrical vessel, the other one is spherical vessel. So you can just go over the one of the problems. 13.3 is a good exercise problem. And then the other half of this chapter, chapter 13, was about the combined loading. When we have the sigma value due to the axial force, and then when we have my over I, or when you have unsymmetric bending, then we have two different moments. So this is basically the main equation for finding out the normal stress due to the normal force, and then this is the term due to the flexure, the moment. So the 13.2 would be the good problem to practice this combined loading. So these two problems from the textbook, and I think the entertainment package problem was included in the previous entertainment package. Okay, so this is pretty simple and straightforward and short chapter 13. Let's move on to chapter 14. So chapter 14 was not covered in any of the exams before, so I can say you will have definitely the problems from this chapter 14. And the topic in chapter 14 was stress transformation. The half of this chapter is about strain transformation, but we did not cover the strain transformation. We just focused on the stress transformation. The basic idea is this. We initially started with the stress block, including all 9 components of the normal stress and 2 different shear stresses. That is a typical, like this. That is the typical, and we do have a normal stress in the perpendicular to the z direction and so on. So these are the total of 9 components of the stresses, and that is the general all normal, including all normal stresses and shear stresses. But in many cases, we can simplify it into 2D model, so that these 3 stresses, the sigma x, sigma y, and tau xy. If you know these 3 stresses, you can easily find out everything, all the stresses on this 2D model. So this is the case we call the plane stress condition. And in this chapter 14, in this level of the class, the strength and material and the undergraduate level, we only talk about this plane stress condition. And there are several different examples and cases that we can apply this plane stress condition. And you can see the video clip for chapter 14. So at the beginning, we talked about, I went through the derivation of the equations, sigma x prime and the tau x prime y prime. The reason that we do this stress transformation is because sometimes based on the given stress condition, we'd like to know what is going to be the maximum normal stress and what is going to be the maximum shear stress, because those maximum value can be used to design the devices or structural system. And we have to make sure that as a designer that we have to make sure that those maximum normal stress and maximum shear stress due to the load will not exceed the maximum capacity, right? The allowable normal stresses and allowable shearing stresses. So that's one of the reasons that we apply this stress transformations to find out the maximum values. So through the derivation, we got these two equations. Sigma x prime is equal to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. And then tau x prime y prime is equal to minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. Okay, so these two equations were coming from the derivation, and then rearranging these two equations. So take this one to the left-hand side and square the first equation, square the second equation, add them together, and we realize that the rearrangement of that equations will provide the equation of the circle format. Okay, so that was in page It was in page 643, equation number 14-11. So it looks something like this. Sigma x prime minus sigma average. Sigma average, by the way, is the sigma x plus sigma y divided by 2. So this square plus tau x prime y prime square is equal to r something squared, and that r looks like this: square root of sigma x minus sigma y over 2 squared plus tau xy squared. So we finally get a certain equation in this form. So we can easily draw a circle to explain this different state of stresses. And by the way, so the name of this circle is called the Moore's circle. And by the way, when we develop the Moore circle, the x-axis is the normal stress sigma. Y-axis, the thing is kind of interesting because this y-axis, the positive direction is downward. Okay, but anyway, this y-axis is based on the tau, the shear stress. So to develop this Moore circle, we have to first identify 3 points. The same notation from your textbook. One is C, that is the center, the sigma average, comma 0. The second point is A. Okay, the coordinate of A is sigma x, comma tau xy. The third point is G, minus sigma, sigma y, comma negative minus tau xy. So you have to first pick and point these 3 points. So first of all, the sigma average, comma 0, that should be on this x-axis. And sigma x, comma tau xy, let's say sigma x is positive, tau xy is also positive. Then we will have something like this point. If this sigma x, then sigma y should be here, and then negative tau xy. So this point should be G. And these 3 points, C, A, and G, should be on the same straight line. It should be on the same line always. So this is the first step. You have to identify these quantities based on the given stresses, sigma x, sigma y, and tau xy. So you can easily find out these coordinates and put those 3 points on this coordinate system, and then develop the circle. Something like this, okay? I know this is not really good, a circle. Maybe better, a little better. So when you develop this Mohr circle, you can easily find out what is gonna be the maximum normal stress. So this is gonna be, we call the principal stresses, the maximum and minimum normal stresses. We can also identify the maximum values of this tau value, tau max. And tau max is always equal to R because this is going to be equal to the radius of the circle. Okay, and this angle should be, so this is the current state of stress to the principal stress, which is the maximum and minimum. And that corresponding angle is, we call the theta P. And the angle change on this Mohr circle is always twice larger than the angle change in the normal space. So for example, when we just change the angle in 30°, then you have to move either clockwise or counterclockwise 30 times 2, the 60°, okay? So that's the basic, the idea of the Mohr circle. And the practice problems for this chapter, chapter 14, would be chapter 14.2, 14.4, 14.8, and 14.9. Okay, so these are the problems from the textbook, and then entertainment package problems. Okay. All right, so the last one, chapter 17. This is about buckling failure. Again, we didn't have the entertainment package from this chapter, so I'm gonna put only one problem as an extra point problem. So it's better for you to just exercise this chapter because you can easily earn the extra point from this chapter. Only one problem. So the basic idea is this: the buckling is the very unique failing mechanism for the columns under the compression only, okay? So the starting point was the Euler buckling equation. I went through all the derivation, and there are some basic fundamental assumptions to develop this Euler equation. One is the boundary condition should be pin and pin boundary condition. The column should be straight, perfectly straight, and the loading is going through the central axis of the member and so on. So finally, we will get the expression piece of CR. So this is the corresponding amount of the force, the compression to buckle the column. So piece of CR is equal to pi square EI over L square. Again, this is only for the case when we have a pin boundary condition. I didn't cover the later chapters in later sections this time, but if you're civil engineering students, we're going to talk about this buckling failure in EGR 352 when we talk about the steel design class. In that case, when we have a different boundary conditions, we're going to go through another factor called the effective length factor K. So the equation is a little bit different. Instead of just L, it's going to be KL, and then we have a different factor of K depending on the different boundary conditions. Anyway, at this time, we are just using the Euler equation based on the pin-pin boundary condition, and this is the formula to find out the critical force, the actual load, the compression, based on the Young's modulus, the material property, the moment of inertia, the sectional property, and the length of the column. So the good practice problem would be example 7.1, and there's no entertainment package. So just go over these example problems. I went through this example 7.1 in my earlier video for chapter 17. So you can go over that video again. Then, so if you're familiar with this problem, then you will get the extra points during the final. Okay, so I think this is all. And thank you so much for taking this class. Again, I'm so sorry that this review session was delayed, but I really appreciate your patience and your hard work, even though we have very unexpected situation through this, due to the COVID-19 situation. I hope you enjoyed my videos, and I hope you learned all those materials and the contents through this semester. And I hope you enjoy the final as well. One last thing that I'm gonna post this review session video under week 16 folder, and there will be one more thing before you leave for the summer that is called the course outcome survey. So which is, at the beginning, you might remember that in the syllabus, that's the contract between you and me, I listed the outcome, the program outcomes, which program outcome is going to be matched and fulfilled throughout this class. Okay, so there were several different goals of this class, and I just want to make sure that we went through all those goals and fulfill all those goals so that you are confident to meet those program outcomes. So that course outcome survey will be available under week 16 folder, and I'll be appreciated if you can complete that survey. All right, so this is final, really the end of the video. Thanks again, and see you on Thursday during the final. Or if you have any questions or comments or anything related to this class, I'm always available via email, or you can ask me to have set up the WebEx session if you want. But we'll see you on Thursday. Bye.